Alright, so let's recall the definition of SD. So what is this? So recall that SD consists of the empty set and collection of all sets of the form A1, B1 crossed all the way with AD, BD, where each AI and BI is an element of R, but could also be plus or minus infinity. And of course, I think it also we have AI is less than or equal to BI. Well, wait, no, it has to be strictly less than. That's not mentioned in the textbook, but it's sort of implied by the way that these intervals are written. So, what else do we have? So we want to show that the sigma field generated by SD is the collection of Borel subsets of RD. So if we use this fancy U, denotes all open subsets of RD. And of course by open I mean open with respect to the standard topology. Then the Borel sigma algebra, do they use sigma algebra or sigma field here? I don't know. The Borel sigma algebra, I'll call it, on RD is just the, by definition, it's the sigma field or sigma algebra generated by the open subsets of RD. So what we're trying to prove is that sigma, or the sigma algebra generated by SD is equal to the sigma field generated by open sets. Because the sigma field generated by open sets is the Borel sigma field. Sigma algebra, whatever. Okay, so now an interesting fact, so if SD is contained in the sigma field generated by U, then, okay, so the sigma field generated by U is the smallest sigma field. Wait. Okay, so let me write this out and then make sure that this makes sense. Okay, so if SD is a subset of the sigma field generated by U, then if we think about the sigma field generated by if we think about the sigma field generated by SD, then that's going to be the smallest sigma field containing SD. And we know that sigma of U is a sigma field which contains SD, and therefore the sigma field generated by SD must contain, no, it must be smaller than the sigma field generated by U. Because remember, when you actually construct the sigma field generated by a set, you take the intersection of all sigma fields containing that set. And so the sigma field generated by U is one of the sigma fields containing SD. So that's one of the sigma fields that you're taking the intersection over. And so therefore, it must be larger than the sigma field generated by SD. And so that confirms that the sigma field generated by that if SD is contained in the sigma field generated by U, then the sigma field generated by SD is contained in the sigma field generated by U. And likewise, if U is contained in the sigma field generated by SD, then the sigma field generated by U is contained in the sigma field generated by SD. Thus, we must prove that SD is contained in the sigma field generated by U, and that U is contained in the sigma field generated by SD, because then this will prove that both the sigma field generated by SD is contained in the sigma field generated by U, and it will also prove the reverse inclusion, and when you have inclusion in both directions, then you have equality of sets. And so if we can prove these two inclusions, then we've proven that the two desired sigma fields are equal. Okay, so let's start this. So to prove that SD is contained in the sigma field generated by U, let S, call it S A1 B1 all the way up to AD BD. Let this be some element of SD. Let U be A1 B1 cross all the way with AD BD. And okay, so basically what we're trying to do here is we want to find, we want to construct S from elements of the sigma field generated by U. And so U, this set that I've constructed here, is a good set to start with because it's clearly an open set, because open rectangles in RD are open sets in the standard topology. That's a fact from basic topology. And so let's see here. So this includes most of the points of SD. Well, most is sort of like a weird word to use. But basically all you're missing is the closed brackets at the end of each of these intervals. And so to include that, well, closed brackets mean closed intervals, so let's try to make a closed set. So let's let V equal, well, we can't just take the closed interval from A1 to B1, because that will extend outside because that will include it will include A1 in the first entry, which is not a characteristic of S. S does not, none of the points in S contain the value A1 in their first entry, first coordinate. So what we have to do here is we have to choose, instead of putting a closed bracket around A1, we have to put a closed bracket around a point that's a little bit to the right of A1. So let's see here. A1 could be, let's see here. So here's what I came up with. Take the minimum of A1 plus B1 over 2 and A1 plus 1 B1. Okay, so this is what I came up with. So the tricky thing here is normally just using A1 plus B1 over 2 would work because that's the midpoint between A1 and B1. And certainly that's going to be to the right of the point A1. However, there's issues if you have infinities. So let's see, if we have if B1 equals positive infinity, then this midpoint is going to be infinity. Well, actually, if B1 is positive infinity and A1 is not negative infinity, then this midpoint is going to end up being positive infinity by the way that this fraction is written. And so then that's not good enough, or that won't give us any points in this interval, and so we have to use, I guess in that case you could just use A1 plus 1. And so that's why I have that here. And of course that one's going to be more further to the left, but still not at A1. However, if A1 equals minus infinity, then we don't really have to worry about it. So we can just use A1, we could just use minus infinity here. And we'll sort of interpret that as being A1 plus 1 in the case of A1 being equal to minus infinity. And in the case of A1 being minus infinity and B1 being positive infinity, we'll just not include the A1 plus B1 over 2 because that's not defined when A1 is minus infinity and B1 is positive infinity. So in the case where this is not defined, we'll just automatically use minus infinity. Okay, so that's a little... So I guess what I explicitly mean here by this closed interval is not technically what I wrote, but I've written this in a way and explained what I mean by this, where hopefully it makes sense. Basically what we're trying to do is we're trying to find a closed interval which contains the right endpoint B1 and which is contained in the half-open interval A1 to B1. That's really all we want here. Okay, and so then we do the same thing over here. AD plus 1, BD. Okay. U is open because it's just a product of open sets. Well, I guess that's... Yeah, that's even a thing in that you have to prove, that if you have like a product space and you have open sets in each of them, you can just take the product of open sets and get an open set. Of course, you have to be careful there, like you have to be working, like it certainly works when you've got finitely many dimensions, but you got to be careful. Anyway, but the point is U is open in the standard topology, of course, and V is closed. So, and that this is true regardless, even if we have infinities in the some of the endpoints, this will still be true. And so, U and V are therefore both elements of the sigma field generated by U. Because remember, not only sigma fields have to be closed under complements. So the sigma field generated by U not only contains all open sets, but it also contains all closed sets, because closed sets are complements of open sets. Okay, so thus, S is U union with V. So it's a union of two sets in the sigma field generated by U, but the sigma field generated by U is closed under countable unions. So this is an element of U. Okay. So we've proven that S is an element of the sigma field generated by U. This holds for all S in SD, and so SD is contained in the sigma field generated by U. This confirms, as we've discussed, that the sigma field generated by SD is contained in the sigma field generated by U. Alright, and now we want to prove that U is contained in the sigma field generated by SD. And this proof is actually going to look a lot like the proof that we're going to use in the next exercise, but we'll get to that. So let U be an arbitrary open set in U. Let script S, or fancy S, be the set of all points, all sets S in SD. Well, actually, no. S is going to be all points of the form A1, B1, cross, all the way with AD, BD, where S is contained in U, and each AI and BI are contained in the rationals. Then S is countable, because each S is determined uniquely by its each element of S is determined uniquely by the endpoints of its intervals, and these endpoints of the intervals, there's finitely many of them, and they're chosen from a countable set, and therefore there's only countably many such sets. Okay. So since S is countable, well, S is a countable subset of SD. And so the union overall sets S in this collection S is contained in the sigma field generated by SD. And that's because sigma field generated by SD is closed under countable unions. Okay. I claim that this union is actually equal to U. And to prove this, let X be an element of U. Well, actually, let's first say, certainly, the union is going to be contained in U because each element of this set S is a subset of U. And so if you take a union of a bunch of these things, you're still going to be in U. And so this union is a subset of U. So for the reverse inclusion, to prove that U is a subset of this union, let X be in U. And we know from topology, just basic point set topology, and I guess it's not technically a requirement for this course, but I would highly recommend, if you haven't seen any point set topology, maybe going through chapter 4 of Falland. Or then again, I don't know. Topology is a nice enough of a course that you should probably go through it separately. Because, I don't know, it's really cool. And it's also really important in analysis in general. Okay, so U, the standard topology on RD, is generated, and when I say generated, I don't mean generated as a sigma field. I mean generated like a topology generated by a set. And that's from the usual topology definition of that phrase. So U is generated by open boxes in RD. And so X is contained in C1E1 across all the way to, and then the reason I use C and E instead of C and D is because we use D for the dimension. Okay. So because open boxes form a base for the topology, a base for the standard topology on RD, we can put X in a open box which is contained entirely in U. Then for each I, choose AI and BI in Q such that XI, wait, do we need these to be in Q? Yes, we do, because we need countability. It's in AI, comma BI, which is entirely contained in CI, comma DI. And I guess you could go through and prove that this is doable, but it's sort of, the fact that CI to DI is an open interval means that there's some space between CI and XI, and between XI and DI, and in that space you can find a rational number and use that to get your AIs and your BIs. And also, I should note here that XI is the ith index of X, the point X in U, because U is a subset of RD, so each point X can be written as using coordinates x1 through xd. Okay. So then X is contained in AIBI cross AD, BD, which is an element of S. Actually, here, let's do it this way. If S is this set, then S is in this set script S, and X is contained in S. So X is contained in the union. Yeah, I guess this wasn't really necessary. You can just, this is all that we need. So X is contained in the union of all the S's. This holds for all X in U. And so this proves that U is contained in the union of the S's, and thus U equals the union of the S's. This holds. So what does this prove? This proves that U is an element of the sigma field, because we've proven that the union of all the elements of S is an element of the sigma field generated by SD. And so U is an element of the sigma field generated by SD, and this holds for every single U in the set script U. And so U is contained in the sigma field generated by SD. And so the sigma field generated by U is contained in the sigma field generated by SD. And hence, the sigma field generated by SD is equal to the sigma field generated by U, which is, by definition, the Borel sigma field on RD. And yeah, that's just because we proved by inclusion, and so you have equality of these sets. And yeah, that's all there is to this exercise. There is some stuff that I used here from basic topology that if you aren't as familiar with it, then it might be unclear where I got some of these facts from, like the fact that the standard topology, which is generated by open balls by definition, is also generated by open boxes. And that's something that you can go ahead and prove, or you can find a proof of it if you want. But it is a fact, and I think at this point I'm not going to be too worried about making sure I prove a whole bunch of the I don't want to go back and redo a whole bunch of topology stuff. I'll just leave that to anyone who doesn't have that background to figure out on your own or go look it up on your own. But I'll sort of assume that knowledge, and whenever something like that comes up, I'll mention that you can find it somewhere else. But yeah, that's about all that there is to this exercise, and so we are done with the proof.